Mid-February 1943, Sidi Bouzid, Mamoun Ahmad. Mid-February 1943, Sidi Bouzid, Tunisia. The captured M4A1 Sherman tank rolled to a stop in the desert sand, its American star still visible beneath the hastily painted German cross. Officers from Heavy Panzer Battalion 501 gathered around this prize, notebooks already in hand. This single American tank, captured intact and operational during the Battle of Sidboid, would trigger a crisis of confidence among German engineers that would echo through their tank development programs for the rest of the war. The mathematics of armored warfare were about to be rewritten, not through superior firepower or armor thickness, but through something the Germans had never prioritized: automotive excellence that simply refused to break. The tank bore the name War Daddy 2 painted on its hull. Serial number USA 367641, built by Lima Locomotive Works and belonging to Company G of the 1st Armored Regiment, 1st Armored Division. Personnel from a German reconnaissance unit drove this Sherman 350 kilos across North African terrain to the port of Spafax, a journey of 4.5 days. Every kilometer revealed something that contradicted German assumptions about American industrial capability. The engine never overheated. The transmission never failed. The final drives maintained consistent performance. German tank crews, accustomed to frequent mechanical stops, even on short movements, watched in growing unease as this enemy vehicle simply worked without complaint through terrain and conditions that would have disabled their own equipment. At the port, War Daddy 2 was loaded onto a cargo ship bound for Germany. The Army Weapons Office had issued explicit orders. This tank must reach the testing facility at Kummersdorf, intact and operational. German intelligence had received fragmentary reports about American tank production, but seeing the physical vehicle made those statistics real in ways numbers on paper never could. The Sherman represented mass production at a scale Germany could not match. Built with automotive engineering principles Germany had not mastered. As the ship steamed northward across the Mediterranean, Wehrmacht engineers prepared testing protocols that would reveal truths they had been reluctant to face about their own limitations and American capabilities. Spring 1943, Kummersdorf Proving Ground, Brandenburg, Germany. War Daddy 2 rolled off the transport rail car bearing the designation Versuchfahrts 259 in German, license plate UH058941 test. Engineers had already stenciled armor thickness, measurements and angles across every surface of the tank, marking it with precise notations for their comprehensive evaluation program. The German Army Proving Ground at Kummersdorf, located 25 kilometers south of Berlin, served as the primary testing facility for both German and captured Allied equipment. Here, meticulous engineers measured, tested, and analyzed everything from track tension to transmission efficiency, documenting their findings in exhaustive technical reports. The Sherman was about to undergo the most comprehensive automotive examination German engineering could devise. German test engineers conducted the initial inspection with teams of specialists from multiple technical branches. They photographed every component from dozens of angles, measured every clearance with precision instruments, and documented construction techniques that seemed impossibly straightforward compared to German methods. The transmission caught immediate attention from powertrain specialists. Where German tanks employed straight-cut gears, requiring precise tolerances and frequent maintenance, the Sherman used herringbone-cut gears that distributed stress across multiple teeth simultaneously. This design standard in American automotive manufacturing since the 1930s provided exceptional durability with minimal precision requirements. German engineers had considered herringbone gears too difficult to mass-reduce, given their industrial capabilities and workforce training. The Americans had been manufacturing them by the thousands. The testing began with basic automotive trials designed to stress every mechanical system under controlled conditions. Engineers drove War Daddy through obstacle courses designed to replicate battlefield conditions, measuring fuel consumption, monitoring engine temperatures, and recording transmission behavior under varying loads and terrain conditions. After each trial, they disassembled components to examine wear patterns, looking for signs of stress, inadequate lubrication, or design weaknesses. The results contradicted everything German tank doctrine had accepted about the necessary trade-offs between performance and reliability. The Sherman performed adequately in every category and excelled in the one metric German tanks consistently failed: operational endurance without maintenance intervention. The powertrain examination revealed design philosophy differences that explained much about American versus German approaches. The Sherman transmission featured 5 forward speeds plus 1 reverse, with synchronization in gears 2 through 5 that eliminated the need for double clutching during normal operations. This made the tank nearly as easy to drive as civilian automobiles, requiring minimal specialized training for drivers. German tankers, by contrast, spent considerable time learning complex double-clutching techniques and careful throttle management to avoid damaging their transmissions. The Sherman's design accepted that ordinary soldiers with basic automotive knowledge would operate these machines, while German designs assumed highly trained specialists would be available. The Continental R975 radial engine in this particular Sherman demonstrated remarkable tolerance for varied operating conditions. Engineers noted that the engine maintained consistent performance across temperature ranges that would have caused German engines to overheat or lose power. The cooling system, though simple in design, proved highly effective. The air filtration system handled desert sand without the frequent clogging that plagued German tanks in North Africa. Every system reflected a design philosophy that prioritized practical functionality over theoretical optimization. June 6th and 7th, 1943, Hillersleben artillery range. Reich's Minister Albert Schaar arrived to preside over a major armament conference attended by leaders from the armaments industry and senior Wehrmacht officers. The demonstration program included hill-climbing trials, comparing German and captured Allied tanks. War Daddy 2 sat alongside the latest German designs, including a Panther IV Diam tank fresh from production and a Ferdinand tank destroyer representing Germany's most advanced armored fighting vehicle technology. Schaar, responsible for German armaments production and personally accountable to Hitler for results, needed to understand what American industry could produce and how German designs measured against enemy equipment. The demonstration would provide answers neither Speer nor German tank designers wanted to acknowledge. The Sherman climbed the test slope smoothly, its manual transmission with 5 forward gears, synchronized from 2nd through 5th, shifting without hesitation, its engine maintaining consistent power delivery throughout the ascent. The driver handled the vehicle with confidence, demonstrating the ease of operation that would become a Sherman hallmark. The Panther followed its more powerful 700-horsepower Maybach HL230 engine, allowing it to match the Sherman's performance, but only barely and with considerably more difficulty. The Ferdinand, massively heavy at 65 tons and technically sophisticated with its electric transmission system, stalled partway up the incline. Speer watched as recovery crews struggled to restart the vehicle, the embarrassing failure occurring before dozens of senior officers and industrial leaders. In his memoirs years later, Speer would write about Sherman capabilities he observed during his inspection tour of Italy in October 1944. He noted that reports on the cross-country mobility of the Sherman had been very favorable with the tank. Climbing mountains, German tank experts considered inaccessible to tanks. He attributed this to the Sherman having a very powerful motor in proportion to its weight, giving it cross-country mobility on level ground that was definitely superior to German tanks. The 26th Panzer Division had specifically reported this advantage. These observations from Germany's armaments minister carried significant weight within Wehrmacht circles. The written public assessment appeared in Das Reich newspaper on June 27, 1943. The article described the Sherman as one of the special accomplishments, of the North American laboratories and called it quite a praiseworthy product of the North American steel industry. The article noted that the first things to attract attention were serial construction and fulfillment of the almost arrogant requirements of the North American automobile industry. The piece mentioned the gyro-stabilized gun as the first attempt of its kind ever to be made anywhere, acknowledging American innovation in this area. These public statements, carefully worded for propaganda purposes to avoid appearing defaced, nevertheless concealed the private alarms spreading through German engineering departments. American tanks weren't just adequate. They were fundamentally better engineered for sustained field operations. Back at Kummersdorf, systematic testing continued through the summer and into autumn of 1943. Engineers measured the Sherman's operational range, conducting extended trials that pushed the vehicle to its limits. They documented operational ranges exceeding 2,000 kilometers before requiring major maintenance, roughly 4 times what early model Panthers could achieve in field conditions. They measured transmission efficiency that exceeded any German tank with power losses through the drivetrain significantly lower than comparable German systems. They examined the synchronized manual transmission that made gear changing smooth and simple, requiring neither the double clutching nor the careful rev matching that German transmissions demanded. The final drives presented another revelation that challenged German engineering assumptions. German Panther tanks employed final drive systems inherited from the Tiger design, a configuration prone to failure under stress. The design used straight-cut gears in housings that proved inadequate for the loads imposed by the 45-ton vehicle. German mechanics in North Africa and on the Eastern Front had reported final drive breakdowns, forcing Panthers to be abandoned after relatively short movements. Sometimes less than 100 kilometers. The Sherman's final drives, built using the same herringbone gear principles as the transmission, rarely failed, even under sustained combat conditions that would destroy German components. Restoration projects decades later would find Sherman final drives that needed no mechanical restoration after years of storage. Testament to design margins that exceeded immediate requirements by substantial factors. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that circulated through Wehrmacht technical branches. These documents, intended for senior Wehrmacht officers and armaments ministry officials, painted a sobering picture of comparative capabilities. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked despite its theoretical knowledge and scientific expertise. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training. While German vehicles required factory-level precision and specialized equipment for many repairs, the entire design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive in specifications but couldn't be maintained in combat. Internal German engineering assessments documented observations about American industrial advantages that went beyond simple production numbers. American automotive engineering reflected decades of civilian industry experience that Germany had never developed at comparable scale. Before the war, the United States had widespread automobile ownership with vehicles commonplace among ordinary citizens across all economic classes. Germany had far more limited civilian automotive experience, with cars remaining luxury items for the wealthy and party elite. The Volkswagen program, promised to German workers since 1934, had delivered fewer than 1,000 civilian vehicles by 1939, this vast difference in automotive industry maturity translated directly into tank design philosophy. Americans built tanks that mechanics with civilian automotive training could maintain using skills they already possessed. Germans built tanks that required specialist training and constant expert attention from personnel with years of specific military technical education. The comparison with German tank reliability became impossible to ignore as field reports accumulated through late 1943 and early 1944. Panther tanks required strict operational restrictions to prevent mechanical failures that would leave them stranded. Drivers received explicit instructions not to change gears frequently, as excessive shifting damaged the transmission. Third gear in particular broke often enough that field manuals warned against its use, except when absolutely necessary. Panthers could not turn while backing up, as this would destroy the transmission. Pivot turns were only possible when ground resistance was equal on both tracks, severely limiting tactical flexibility. Foreign objects entering the running gear could jam the drive sprocket, requiring hours of maintenance to clear. These problems existed despite Panthers being built in dedicated tank factories by skilled workers using the best available materials Germany could provide. The Sherman, by contrast, had been designed by automotive engineers at General Motors, Ford, and Chrysler, applying mass production principles they had developed over decades of civilian vehicle manufacturing. The tank incorporated commercial automotive components wherever possible, leveraging existing supply chains and manufacturing expertise. The transmission came from multiple manufacturers, including Caterpillar Tractor, Buick, and Ford Motor Company, all building to identical specifications with fully interchangeable parts that could be mixed freely without adjustment. This standardization, routine in American automotive industry, remained largely theoretical in German tank production, where each manufacturer introduced subtle variations that prevented true parts interchangeability. Additional captured Shermans arrived at Kummersdorf through 1943 and 1944, including tanks taken from British units in Italy and Soviet forces on the Eastern Front. Each captured vehicle underwent similar testing protocols, building a comprehensive database of American tank capabilities across different variants and production periods. The British had refitted some Shermans with their 17-pounder anti-tank gun, creating the Firefly variant that addressed the Sherman's main weakness in firepower. German engineers examined these modified tanks with particular interest, noting how the Sherman's large turret ring accommodated the significantly larger gun with minimal modification. The Firefly demonstrated growth potential built into the original design that German engineers had not considered when specifying their vehicles. The Panther, rushed into production to counter Soviet T-34 tanks, had no capacity for significant armament upgrades without complete turret and vehicle redesign. The automotive testing program expanded to include reliability trials specifically designed to replicate combat conditions. Engineers drove Shermans through hundreds of kilometers of cross-country movement, recording every mechanical incident, maintenance requirement, and component failure. They compared these results with field reports from Panther and Tiger units operating on the Eastern and Italian fronts. The numbers told an unambiguous story about comparative reliability. Panther operational readiness averaged below 40% through most of 1943, with some units reporting catastrophic rates as low as 20 to 25%. Individual Panther battalions documented periods when fewer than 1 in 5 tanks were actually capable of combat operations. By comparison, Sherman tanks maintained substantially higher operational availability across all theaters. Specific data from German field reports documented Panther reliability problems in devastating detail. In July 1943, during Operation Citadel at Kursk, Panthers achieved only 16% operational readiness, with mechanical failures eliminating more tanks than enemy action. By December 1943, readiness had improved to only 37%. February 1944 reports showed 37% operational. April 1944 reached 50% operational. May 1944 finally achieved 78%. These figures represented the percentage of Panthers that were actually capable of combat operations on any given day, with the remainder broken down awaiting parts or undergoing repairs. The progression showed gradual improvement as design flaws were addressed, but even the best Panther readiness rates never matched what Shermans achieved from initial production. By December 1943, the pattern had become undeniable to any objective observer examining the data. Engine lifespan for the Sherman diesel variant exceeded 3,000 kilometers under proper maintenance. Panther engine lifespan barely reached 1,000 kilometers, even after improvements addressed the worst early problems. German reports from March 1944 documented that improved Panther engines achieved service life of 700 to 1,000 kilometers, presented as a success. This improvement merely brought Panther engines to roughly 1/3 of Sherman diesel capability. Sherman transmissions required minimal maintenance between overhauls with synchronized gears that made driver error less likely to cause damage. Panther transmissions demanded constant attention and frequent repair, with third gear failures, so common that drivers learned to skip from second to fourth gear to avoid using the problematic ratio. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation. Field reports from German units using captured Shermans reinforced the Kummersdorf testing data with real-world operational experience. German mechanized units desperate for reliable vehicles, as their own tank infantry degraded eagerly employed any captured American tanks they could obtain intact. Unlike Soviet T-34 tanks, which Germans modified extensively before use, Shermans entered German service without changes. They didn't require modification because they worked correctly as designed, with no fundamental flaws that needed correction. German tank crews, who had experienced multiple mechanical failures in their own vehicles, found the Sherman's reliability remarkable and frequently commented on it in letters and reports. Reports from Panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness, while Panther and Tiger crews constantly worried about reaching the battlefield without breakdown or completing missions before mechanical failure immobilized their vehicles. The 10th SS Panzer Division captured 12 M4A3 Shermans at Hillersleben in January 1945 during Operation Nordwind. These tanks had belonged to the American 43rd Tank Battalion and were captured intact when their